All right, so we are talking about technology of 2030. So our space of distributions are just, you can consider it as some points, P and Q. So they're extremely difficult, and because they live in infinite dimensional space, they're extremely difficult to represent it. So we just map it to a Hilbert space, which is the trick that we do in functional analysis. And so we map it to some other points, which are in Hilbert space. And because in Hilbert space, you can consider it as a linear space. So it's a generalization of Euclidean space, this Hilbert space. So you can do lots of embeddings, decompositions, anything, almost anything you do in linear algebra, you can do it here. And of course, much more general than that. So the idea is that, for example, the P distribution is something like the multiple modes, very extremely difficult, sometimes discontinuous. So from here, there is no probability. Again, there's something discontinuous and non-differentiable happens. So you can code such a complex non-differentiable or differentiable distributions into another space, which is much more easier and better, and could be represented by some other spaces, which we call it Hilbert spaces. And so I mapped any distribution. By distribution, I mean density, probability density function. And we are not talking about cumulative distribution, which is something like this. It goes to 1 at the end. But here, I mean, by talking about distributions, I'm talking about probability density functions. So this is the trick that we use. We map it. So for each P, we have an equivalent point, which is infinite dimensional in general, in the Hilbert space. So topological spaces are very general, but topological spaces are very, very general. We cannot do anything about it, so we go to metric spaces. We define a metric. And then Banach spaces are spaces which have norm. So not only you have metric, you have a norm as well. And Hilbert space is rather more better, because not only you have a norm, you have an inner product, but it is less restrictive than Euclidean space. You do linear algebra here, but sometimes, for example, in quantum mechanics, you cannot do simply just some linear algebra. You do you work on Hilbert space of some functions, for example, states of quantum mechanics, psi functions, and you have some operators, and these operators they work. You can apply it on your functions, which are in general infinite dimensional. And so because the space of functions, for example, in quantum mechanics is infinite dimensional, we cannot parametrically just say it. For example, you can say all spaces that live inside these two bounds, lower bounds and upper bounds. For example, this could be one function, this could be another function, this could be another function. So in general, they are infinite dimensional. There are infinite possibilities that you make a function between them. So that's why we are interested in Hilbert spaces. But in Hilbert space, but here, when we define that distribution like this, that I talked about, that here you should look at it as a Bochner integral. So the values of Bi are not constant. They live in a Banach space. They live in a Banach space. So mu is the measure, if you're familiar with measure theory. So you can write it like this. It is, so it's a generalization of Lebesgue integral, if you're familiar with. Bochner integral is a generalization of Lebesgue integral because the values live in a Banach space. So you can consider it as, for example, if this is a function, you try to estimate it using some simple functions. You try to estimate it, okay? But unlike Riemann integral, it is the supremum. It is not, these are not equal ranges. It could be, for example, S1, it could be S2. S2 is not equal to S1 in general. So this is the idea of Lebesgue integral. But in Bochner integral, these values, they live in Banach space. Kernel characteristics. These are the knowledge that is created by Fukimizu and Bernard Schopf and Max Planck, and we just review it. So if it is a kernel is called characteristic, if it is injective, think about as a one-to-one mapping, so that if this equation holds, then those distributions are equal. A very famous and practical Gaussian kernel is Gaussian, and after that Laplace. And I don't like polynomial kernels because they're not characteristic. And there is an application of Riesz representation in general Hilbert space, that if you have if H is a Hilbert space and phi lives in the dual space, it could be a space of functionals, it could be a space of operators, it could be anything. Then there exists an F that you can represent it with this. It says that if phi is a functional, so by means of functional, it maps a function to the R, any function. So if you have found such a phi, such a functional, for each x, if you have found for each x this relationship holds, then there exists a unique F inside Hilbert space that this equal. This is the Riesz representation theorem. So I told you that you can represent those distributions with mu p, which we defined it as integral of some feature maps, let's say phi of x, dp of x. So you can understand that you can apply the Riesz representation theorem. Why Riesz representation theorem is going to? Because EP of f is a functional. So for each f, this functional has this relationship. Okay? So there exists one embeddings, let's say one mu inside the Hilbert space. Remember that those distributions are just some points in our complicated space of distributions. But here, it is the Hilbert space. So we map it to mu p. We map it to mu q. So here, the Riesz representation theorem says that there exists a unique mu, and unique representation, such that for all functions in that Hilbert space, this inequality will hold. Another example, if you're talking about conditional expectations like this, you can have, you'll see a little bit that we could use Riesz representation again, because you say that there exists a unique element of the Hilbert space that you can define a relationship like this. And Mercer equations, Mercer kernels. Let X be a compact Hausdorff space and mu be a finite Borel measure. Suppose K is a continuous positive definite kernel, and define the integral operator by this. This is the integral operator. So you give F from Hilbert space, the operator gives you another function in the Hilbert space. So there is an orthonormal basis such that you can represent that here. But in general, I told you that you cannot find, we do not usually find the feature map that you see explicitly like here. We think about it, we think about phi as some implicit mapping, because it is very difficult that, for example, you have an image, it has 1,200 pixels, so it is 1,200 dimensions, and you cannot define this big feature map. So you work on that like an implicit map, and you'll see what I mean. So let's review. This is the classic kernel that we use, for example, in support vector machine. We can use it for principal component analysis. And this is the old-fashioned, so it is for 2000, and 2005, and in 2012 or 2020, we look at the mapping like this. We map distributions to some points, some infinite dimensional point in the Hilbert space, and I guess in 2030 we will use a combination of all of them, 1 and 2 and 3. If it is 1, 2, and the third approach, third paradigm. So when we combine these paradigms, you will see it in 2030. So this is pretty much the idea. And one lemma from Smola and Bernard, which are the pioneers of this area. If this expectation is finite, then mu is inside Hilbert space, and more generally we can have such again some using some Riesz representation, as I told you before. So we use Jensen inequality. Jensen inequality is about expectation of convex functions, and then use Riesz representation theorem. And finally, you can do all of these achievements using some empirical embeddings. In practice, we finally approximate it. So if this is P and Q, we approximate it by mu of P, mu of Q, If P is a real thing that we don't know, real distribution that we don't know, we approximate it, so their difference should be as small as possible.